Okay, I think maybe we can start today's class. So, as we know, this will be the last class of this course. So basically, the last week, that is the this last fourth week of the class, basically they have taught, I think, about the bioinorganic uh, bioinorganic materials and how the metals are working in coordination with the enzymes or proteins and how the body utilizes them. So the problem solving, I don't think we need a problem solving session for that bioinorganic part because the assignment questions are pretty straightforward. So what we will be doing, we'll be solving some state term related, the spectroscopic state term related questions, and we'll just go through the overall course. We'll solve some sample questions. Then if you have any doubts, we will deal with that. So I'll share my screen. So if you have any doubts, you can stop me at any time. And if you're not comfortable to speak up, you can put it in chat box. When I open the chat box, I'll see the text and I'll reply. So I'll just share my screen.
Ma'am,
Yeah.
for the week 4 assignment, there were many questions that were like not discussed in the sessions, in the lectures that sir taught. So, do we have
Okay.
to just remember the answers what are given, or we have to understand the meaning for it, what it was?
Yeah, I saw the assignment questions, so it was like pretty straightforward. Like they were asking what kind of enzymes have this iron or cobalt, or I mean not cobalt, iron, copper, and what is the function of magnesium 2 plus, those kinds of questions. So sometimes I've seen that in NPTEL courses they sometimes take directly from the assignment questions, but um, if that's the case, you have to remember these all these bioinorganic related things. There is no easy way to learn that. You have to remember those, like which enzyme has which metals, like that. But I don't think there will be more many questions from the bioinorganic part, because the other part, which is this problem solving session, like the crystal field theory, the finding oxidation state, spin orbit, the spin orderly magnetic formula, all those things I think will have more weightage. But you should not neglect the bioinorganic part. You can learn as much as you can, but uh, it is just a by hearting thing. There is not much, direct. We can't learn it by understanding it. Some things you have to remember, like which enzyme has which metal and so on.
Okay, ma'am.
Yeah, and I have seen that the week one assignment questions does not have. Uh, I mean, the week one assignment questions have some questions which are not at all related to the whole course, like the number of metal-metal bonds in the organic complex. That is actually not related to the transition metal complexes at all. That is related to organometallic clusters. So for this course, you don't need to know that equation also. So I don't think you have to learn that, because I thought maybe it will come in fourth week, but in all the 4 weeks, it's not at all speaking about organometallics or the clusters. So you don't have to learn that how many number of metal bonds will be there in a complex or something. Then another thing I noticed was basically that week one assignment questions, most of it were unrelated to the whole course. So I don't know why those questions came like that. And then some associative, dissociative pathways also, the reaction mechanisms. So these things also were not discussed in the course. So those things you don't have to study, because when the question paper comes, I don't think they'll ask all these out of syllabus questions. They are going to focus on what sir has taught in the class. So you can focus on that basically. So I'll yeah. You have some doubts?
Ma'am, I just want to ask that week 2 and week 3, what we did was really important in this course, right?
Yes, yes, yes.
Oh,
And those, how we are finding the oxidation state, number of unpaired electron, those information will be helpful in your other courses also. Like there will be a continuation of continuation in the organometallics. Then you will study about clusters, or where all these places you will be still calculating oxidation state, number of unpaired electrons, the spin orbit, spin angular momentum, all those things. So whatever you learn in that second and third week of this course is the most important part of this course. Also, I think second week had something like, but the first week content is important. First week assignment questions are not important. First week content was something related to electronegativity, how the trend of metals or the elements are changing along the periodic table. Then there was something, I think, electron affinity, how it is changing, ionization potential, how it is changing. That first week content will be helpful for all the courses that you take, because that is general only. So first week content is very important, that you should not miss. But as per this course, second and third week content is much more important, because we are first we are learning how to solve these oxidation state. We are understanding these metals, and whatever information that we studied in this course will be utilized for other inorganic chemistry course, like organometallics or clusters, or then there'll be catalysis and so on and so on, like in your BSc and or MSc. Yeah. Um,
Ma'am, basically in the week two course also there were some equations that were given by sir. So are they also important, or the one that we did in the class was that's it?
what were the equations? Can you
Uh,
remind me?
One
Like
second.
related to what?
Ma'am, it was related to something thermodynamics, thermal energy, and some equations were there, how it changed.
Uh-huh. Okay, so how we are refining the metals from the metal oxides.
Yes,
That is
yes.
also important. But as I said, bioinorganic part and this metal refining part is like a, if we divide this course, basically it has two parts. One is a general part where we have discussed the trend along the periodic table, how we can refine a metal from its metal oxides. Then this thermochemistry related like equations that you were talking about, and the bioinorganic part. These all are um, applications and how we utilize the metals. The other part is the actual chemistry of the metals that we are interested in. So both are important, but I would say you give more preference to the second part, because that there you have to practice those questions, then only you'll be able to answer it. The first part is more or less, if you understand it and sometimes some things you have to remember, then you'll be able to answer the first part. But the second part is, if you can't, if you practice it very well, then only you will be able to write. Just by looking at the question without practicing, if you go to the exam, you won't be able to write it. So you have to practice all the problems that we have discussed in the problem solving session, as well as in the assignments that they have given. And if you take some normal inorganic chemistry textbooks, there also you'll find many questions. So the more you solve, the more you will get experience, and then you'll be able to solve in question paper. The question paper will not be very hard, it will be a moderate level exam. So
Ma'am, where
practice
we
the
can get
second part.
the sample papers, how the exam is going to be, what are the marks distribution and so.
That I don't have any idea. You can actually mail the NPTEL coordinators, or there are actually other TAs for this course. I am actually not related to this course. I am only for these problem solving sessions. But there are other TAs who are taking or handling the course, and they are putting the assignment questions. So I think there is a discussion forum there you can ask, and they will reply.
Okay.
Okay, so maybe today we'll start with this week's content. I'll just share my screen. So my name is Annette Mariateri. I'm a PhD student in the Department of Chemistry at IIT Tirupati. So this is my mail ID. If you have any doubts, you can always contact me. So first we will look at um, the term symbols. After that, we will just solve some sample questions through like that we have discussed in the last classes and all. Then I think it will refresh our memory, and you will be able to write the exam also properly. So first, I'll just give an introduction about what is term symbols, what are term symbols. So basically, the term symbol notation is 2s plus 1 Lj, where this S is the total spin multiplicity, and it is normally calculated as n into half, where n is number of unpaired electrons. For example, let me say P3. P3 is my configuration. So I have, this is my configuration. For this one, I have 3 unpaired electrons. So S will be 3 into 1 by 2. So 3 by 2. So this 2s plus 1, the total, the total spin multiplicity will be 2 into 3 by 2 plus 1. So it will be 4. So this will be the so when we notate it, it will be like this 4lj. So this is what this means. So generally I think you'll be able to see 2s plus 1 is equal to 1 or 3. This state is called a singlet state. This is called a triplet. So I think right now you will be mostly seeing this singlet or triplet states rather than these 4 or other higher states. Then this L can have values from L1 plus L2 to L1 minus L2. So if say for example I have P2 like this. So let me use another color. So for yes, any electron in s orbital, this L value is 0. For any electron in p orbitals, L value is 1. For any electron in d orbital, L value is 2, and so on. So in that case, if I have like this P2, then my capital L will be L1 plus L2 to L1 minus L2. So there are 2 electrons. So this this means modulus. So even if we have a negative value, we'll just take the positive of it. That's what this modulus means. And we have, for each electron, we have to give 1. So 1 plus 1 to 1 minus 1. So 1 plus 1 is 2, then 1 minus 1 is 0. So this 2 means between this we have to subtract minus 1 until we get this value. So it was 2. So, and the final value is 0. In between, there is only one value if we subtract, right? So if my L value, this L1 plus L2 value was 3, let's say 3, and my final value is 0, then in between I'll have 2 and 1, right? Now, J is L plus S. So if I have my S is, so yeah. So for each S, we can have a separate L value, separate J value, and so on. So when we solve the questions, I think it will be much more clear. So we'll start solving some questions. Let me start with this one. So here, the question is for the electronic configuration 1s2, 2s2, 2p4, two
Ma'am,
of the
can you
possible,
please zoom the screen?
yeah, what?
Ma'am, can you please zoom out the screen?
Screen.
Yes, ma'am.
Okay, actually, if I do that, now is it better?
Yes, ma'am.
Okay. So the question is for the electronic configuration 1s2, 2s2, 2p4, two of the possible term symbols are 1s and 3p. So already they have said that we have two possible term symbols, which is 1s and 3p. And what is the remaining term? So first we'll just, okay, one thing to note here is that whenever the orbital is completely filled, we don't have to consider that. We'll only consider the unfilled orbitals. So here the unfilled orbital is 2p4, right? So we'll just consider that. So 2p4 means there are 4 electrons in 3 p orbitals, and we can arrange in many different ways. And you also know that the p orbital has different ml values, that is plus 1, 0 and minus 1. So I'll just, this is plus 1, this is 0, this is minus 1. So I have four electrons, and each orbital can have two electrons at the maximum based on Pauli's exclusion principle. So let me see how many possible arrangements can I have. So either it can be one in each, and it can be paired here. So here the L value will be what, plus 1 into plus 1. This is for each electron, this is the value. So plus 1 plus plus 1, it is 2. Then here it is minus 1. 0, 0 is just 0, right? For one electron, the contribution is 0. I mean, the electron in this subshell orbital is 0, the contribution. So basically L is 1. And for L is 1, we have P. Where L is 0, we have S. Then D, F, and so on. So for this one, the L is P, right? Then we can have similar arrangement where 1, 2, 3, and 4. This is also, if you look at this, we will get minus 1. This minus 1 and plus 1 are equivalent contributions. So this will also be P. Then we can have 1, 2, 3, 4. This kind of configuration is also possible. Here, what will be the L? 1 plus 0 minus 1, right? So it will be 0 basically. So this can be S. Then what else is possible? Then it can be like this. Two electrons in plus 1, 2 electrons in 0. So here L will be 2. So this can be D. And similarly, there will be another configuration where no electron in the plus 1 state, like this. So here also we have D. So basically we can have P, S, and D, right? One second. Okay, I think it is frozen. Let me reshare the screen. Just give me a moment. Yeah. So we can have basically how many configurations? Okay. So we can have S, P, and D, the L values, right? And now let us look at what kind of 2s plus 1 values we will get. So as I said, we have plus 1, 0, minus 1 state, and we have 4 electrons to fill. So either we can do like this, where the S will be 2 into 1 by 2, which is 1, right? Here. Because as I said, S is calculated as n into 1 by 2, where n is the number of unpaired electrons. So this is number of unpaired electrons is 2. So 2 into 1 by 2 is 1. So now the 2s plus 1 value will be 2 into 1 plus 1, which is 3. Now for that, the other case where here also we'll get same value. So this is Same. Now we can have like this. So here also, if you look at the number of unpaired electrons, is the same. So basically, for all this configuration, we will have s is equal to 1 and 2s plus 1 is equal to 3. Now let's look at the other configuration where all were paired. So here s is equal to 0 into 1 by 2 because there are no unpaired electrons. So basically s is equal to 0. So 2s plus 1 is equal to 2 into 0 plus 1, which is 1. So the 2s plus 1 values can be either 3 or 1. So now let's look at what the options were. So they have said that already 1s and 3p are there. So we have also identified that we can be 1s and 3p is there. So before that, let me show you for each S state how the L is changing. Okay, so for as we did, S can be either 1 or S can be 3. So S is equal to 1 means what? Number of unpaired electron is 0. Here number of unpaired electron was 2. So for this state, for n is equal to 0, it should always be paired, right? So it can be like this or it can be like this. For this, we already identified this kind of configuration was seen for what L, D, right? So this kind of configuration was seen for D. So this is basically for n is equal to 0, it can be D. So basically 1D is possible. Then for n s is equal to 3, which means that there are two unpaired electrons. In that case, it can be like this or like this. These are similar only, or like this, right? So in this case, for this configuration, what was the L state that we have identified? P, right? So this was P, and one more we identified, that was S. So this was P and this was S. So we can have 3P and 3S as well. So let us see in the question, 1S, 3P was already identified. Then from the options, it is clear that 1D is the one, right? So we have also identified another state is possible, that is 1D. So from the options, we can identify this. So I don't think they'll give this 2p4 configurations most of the time because this is a bit more lengthy if you have to solve. Most of the time they'll give like 2p2 or 2s1 kind of configurations. So is this so whenever we get this, we have to first find out how many configurations are possible, and for each configuration what will be the L corresponding S and so on. Is it clear?
Mom, can you please explain it once again?
Okay. So here, as I said, for the completely filled orbitals, we don't have to find out the terms of this. We'll be looking only at the unfilled orbitals. So partially filled orbitals. So here it is 2p4, and 2p4 means I have basically 4 electrons to fill, right? And
Yes, ma'am.
these, yes. So p orbital has 3 m states corresponding to plus 1, 0, and minus 1. So I can arrange these electrons in any way I want if the Pauli's exclusion principle is satisfied. Pauli's exclusion principle states that only 2 electrons can be in one orbital. That is a very simplistic way of Pauli's exclusion principle. So we can arrange the 4 electrons in whatever way we please, um, but only 2 electrons maximum in one orbital. So these are all the possible configurations. I am not saying that this is a stable one or this is a stable one, but the electrons can be like this. So there are different configurations possible. Now, if I keep my two electrons here, so 1, 2, 3, and the fourth electron as paired, for each electron in this plus one state will have one contribution, right? Because each electron will have plus one. So there are two electrons. So 1 into 1 plus 1 into 1, it will be 2.
Yes.
Yeah, and 0 into 1 is 0. So we are not, I have not written it. Then minus 1 into 1 will be 1. So 2 minus 1. So L here is 1. So L1 is equal to 1 corresponds to P. So this is a P term, this one.
What does the P in this mean?
So we write, like 2s plus 1 Lj. So this
Hmm.
L here is P. So here I can like this. See 3P. So 3 is here 2s plus 1. This P is basically the L value. It means that L is equal to 1. And
Okay.
this is also a equivalent configuration because just the sign is changing. See 1 plus 0, then it will be minus 2. So 1 minus 2 will be minus 1. So 1 and minus 1 value magnitude is the same. The minus 1 and this plus 1 is there because of the directionality. Because all these are vector quantities, just direction is changing. So for both quantities, it will be same L, same P, right? So both are
Okay.
equivalent, so it is P. Now we can arrange two electrons in the zeroth state. So it will be 1 plus 0 into 2 minus 1, right? So 1 and 1 will cancel out. So basically we have 0. And for L is equal to 0, we have S.
Yes.
Yeah. And then we can arrange two electrons in both orbitals. So 1, 2, 3, 4. So this will be 1 into 1 plus 1 into 1. That will be 2. And 0, 1 in, for each, this will be 0, right? So 2 plus 0, that is 2. So 2 will be,
Ma'am, we could have taken those two electrons in the minus one also, na? Then also it will
yes,
be
that
two,
is,
right?
yes, here I have taken. So 0 into 2 plus minus 1 into 2. So it will be minus 2 and L is equal to and L is equal to minus 2 as I discussed here are equal. So both will have a D, D term. Is this part clear?
Yes, ma'am.
Okay. Now we will see how many spin states are possible. So how many number of unpaired electrons are possible. Either we can arrange two in one orbital, then we can have this configuration, right?
Yes.
Two unpaired electrons. So this is possible in these states that we already discussed here. Like here also it is possible, here also it is possible, here also it is possible. So basically P and S will have this two unpaired electron situation.
Yes.
You understood, right?
Yes,
Here,
ma'am.
here also unpaired electron, two unpaired electrons. So this is, so for both these cases, unpaired electron can be two. Now, um, then it can have paired electrons, two each. So in this case, there is no unpaired electron, and that kind of configuration is seen for this D, right?
Yes. Yes.
So they have already identified 1s and 3p. Now we have to identify one more that we have already identified, no? Because for 1D is here, no? Just now we discussed.
Yes.
So when S is equal to 0, 2s plus 1 is equal to 1, that kind of configuration is seen for D. So 1D is the right answer. So whenever you get this kind of question, you have to like write down and see what kind of configurations are possible, and then you will be able to answer. But this is a bit lengthy question. I don't think you will get it in exam. Most of the time it will be S1 or P2 kind of questions.
Okay. Yes,
Okay,
ma'am.
is it
Understood.
clear?
Yes, ma'am.
Okay. Now we'll solve one more question regarding this. Ah. So now another thing that you have to note is when we have multiple spectroscopic terms, for example, let's say like this, we have 3D, 5S. 3f, maybe 1s, 2f, and so on. So if we have to arrange these in energetic order, that means which one has higher energy, lower energy, how will we identify that? So whenever this 2s plus 1 value is large, is highest, this will be more stable, which means that if I compare 3s versus 1s, 3s will be much more stable. So if I have to write the energy in base of energy, I can say that 3s is much more stable than 1s. So is this clear, this 2s plus 1 and how it's affecting the stability? The energy. I should not stay stable. Energy. Whenever the 2s plus 1 value is the highest,
Greater, no?
yeah,
Ma'am, 3s would be greater, no?
yeah, no, no, no. So here, actually, why this 3s is coming? So 2s plus 1 is equal to 3. That is this state, right? So basically 2s is equal to 2, s is equal to 1, right?
Yes.
So this means that there is, and s we already know s is equal to n into half. So 1 is equal to n into half. So n is equal to basically 2. So there are two unpaired electrons, which means that two degenerate states is there. But in the case of 2s plus 1 is equal to 1, it means that there is only one degenerate case. So whenever the degeneracy increases, the energy of the whole system decreases. That concept is coming here. So whenever this 2s plus 1 value is more, then the energy will be low. Is
Okay.
it clear? Okay.
Yes, ma'am.
Okay. So now next thing to note is, what about L value? Say I already have, I said that when we compare 1s and 3s, this will be the case. But what if my question is 3s and 3p? So among this, who will be having the lowest energy? Here you have to look at again, whenever L is high, the energy will be less. So in this case also, it will be like this. Is this clear? Whenever L is high, energy will be less. Here also the same degeneracy kind of thing comes. Whenever L is high, the more degenerate states are there. That's why it is much more. It has much more lesser energy than the other state. So I'll write it properly. 3p is less than 3s. These two are clear, right?
Yes, ma'am.
Okay, now the J value. J value, as I said, is L plus S. So whenever I have a partially filled, like half filled or less than half filled state, for example, P3, it is a half filled state. In this case, less than half filled state, I should not say P3. One second. Let's say P2. So this is less than half filled. In this case, we will take the lowest value of J. For example, uh, this is 3s 1 by 2, 3s 3 by 2, and so on. In this case, if my orbitals are less than halfly filled, then lowest value of J will be the lowest energy. In this case, like this, because j 1 by 2 and j 3 by 2. 1 by 2 is much lower than 3 by 2. So whenever my orbitals are less than half filled, then the lower value of j will be having more stability. But if it is like P4, more than half filled, in this case, the opposite. This 3 by 2 will be having lesser energy than 1 by 2. And what if it is the same? This P3. In this case, you'll most probably have only one J value, so that you don't have to compare. So whenever there is a half fill state, you will only have one J value. You don't have to. You won't be able to. I mean, you don't have to compare. But whenever it is less than half filled, then you will have multiple J values. Then you will go for the lowest J value because it is less than half filled. And whenever it is more than half filled, you will go for the highest J value because this will be more stable in this scenario. So is this clear?
Yes, ma'am.
Okay. So now we will solve the question. The lowest
Ma'am, this
energy term.
happens
Yeah.
only in the orbitals where there is a lack of electrons, right? If they are fully filled, then it is not possible. No?
In fully filled also, this rule will be applied because it is more than half filled. No? So in that case also, highest J will be having more. Highest J will be having lowest energy.
Okay.
Okay. So here lowest they have asked the lowest energy term for the D8 configuration. So as you know, the D8 configuration is a huge configuration. We have like 8 electrons, we have 5 subshells. If we have to write all the configurations, it is not possible. So let me give you a like a easier way to do this. So one second. Let me resolve this. Okay, so for the D8 configuration, basically we have all these subshells. It can be like this, or different configurations are possible. So different L values are also possible. So it is very difficult to write all these configuration. Instead, another way around is look at the options and look if these are possible or not. So the easiest first we will look at the this 2s plus 1 values. So here there are two 2s plus 1 values. Either it can be 3 or it can be 5. So let us check if 3 is possible or not. So 2s plus 1 value is equal to 3 means what? 2s is equal to 3 minus 1, which is 2. So 2s is equal to 2 and s is equal to 2 by 2, which is equal to 1. So now we also know s is equal to n into half. So s here is 1, right? So 1 is equal to n into 1 by 2. So n is equal to 2. So there are two unpaired electrons. So from this configuration itself, we can see, okay, this is possible. This two unpaired electrons equation is possible. So definitely this 2s plus 1 is equal to 3 configuration is possible. So this can be possible, this can be possible, and this can be possible. Now let us look at if 5 is possible. So 2s plus 1 is equal to 5. It means that 2s is equal to 5 minus 1, which is equal to 4, and 2s is equal to 4, and s is equal to 4 by 2, which is 2. So from this equation we can say 2 is equal to n into half and n is equal to 4. So there should be 4 unpaired electrons. So now you should tell me if 4 unpaired electron is possible. One second. If 4 unpaired electron is possible for this systems, for D8 configuration, is 4 unpaired electron possible? Let me check the chat box. Can you put it in chat box? So is 4 unpaired electron possible for D8 configuration? Yeah. So 1%. Yeah, yeah. Good. So, as you have rightly said, that is not possible because see, we have 8 electrons and we have 5 orbitals to fill. So, somewhere we have to doubly occupy this. So, there is no way to have 4 unpaired electrons. So, this option will not be there because this 2s plus 1 is equal to 5 is not possible. So, we can eliminate that. Now, the question is, what is the lowest energy term? So as I said, whenever we look at the lowest energy term, we will always look at the 2s plus 1 values first. First we'll look at the 2s plus 1 values. But if we did not solve this like this, we will first look at 5s and we will say that, okay, 5s means that the highest 2s plus 1 value is 5 here. So this will have the lowest energy, but this will be the wrong answer. So first we will just look at if this 5 is possible or not, 3 is possible or not, then we will compare with the others. So now then we looked at, then we understood that this 2s plus 1 is equal to 5 is not possible, right? This is not possible and we have eliminated this option. Now our options are 3D, 3F and 3P. For all this 2s plus 1 is equal to 3 and this is okay, right? So, and since they are same for all, now we can't compare, right? But we can now compare the L values. As I said, whenever L is high, energy will be low. So here the highest L value is for F and then for P, no, then for first highest L values for F, then for D, then for P. So the order will be 3F less than 3D less than, 1 second, 3F less than 3D less than 3P. So the lowest energy term is 3F. Is this clear?
Ma'am, can this be possible like that there will be different values for a 2s plus 1 and they are possible for the configuration?
Yeah. So if we have, say, okay, let's assume a scenario where this 2s plus 1 is equal to 5 was also possible. In that case, you can directly take that this is the right option because 2s plus 1 value is highest for 5, so definitely this will be the lowest energy term. But when we look at the options, you should be careful. Just by looking at 2s plus 1 values, you should not jump and select that because sometimes it may not be physically possible. So just check that, and if that is okay, then you go for the highest 2s plus 1 value. Then that will have the lowest energy.
Okay.
Okay. So I hope it is clear for all. I'll just check the chat box. If anyone has any doubts in this question, because after this we'll move on to just refreshing whatever we have studied in the last 2 weeks. Okay, so I hope no one has any questions. Okay, so we'll just move, move on and then we'll discuss, we'll refresh our memories. Okay, so this one you should, um, first I think I'll ask you stepwise. So put it in chat box. What is the oxidation state of Ni here in option A? Oxidation state of Ni, nickel. Okay, okay. Yeah, someone has raised a hand. Sujada, do you have a doubt? Okay, so everyone has said plus 2 as the oxidation state. So let us just solve. So as we have 4K outside, so the overall complex's charge will be nickel Cn6 4 minus. So now we'll solve x plus minus 6 is equal to minus 4 and x is equal to minus 4 plus 6 plus 2. So this is indeed plus 2 state. Now what is the oxidation state of nickel in option B? Please put it in chat box. What is the oxidation state of nickel in option B? Okay, okay, okay. So let's discuss. So here also 2 K is outside. So the overall charge will be 2 minus. Now the oxidation state will be x minus is equal to minus 2 and x is equal to minus 2 plus 6, which is plus 4. So this is plus 4, right? Now what is the oxidation state of nickel in option C? Please put it in chat box. Okay, okay, great. So you are absolutely right. The for in option C, nickel has zero oxidation state. Take this. Yeah. So there is no charge. So this is basically no charge on the complex. So X, and for carbon monoxide is also a neutral ligand. So there is no oxidation state for that, no charge for that. So this is like this. So X is equal to 0. So this is 0. Okay, now what is the oxidation state of nickel in option 4? Please put it in chat box. Okay. Okay. Yeah. So we'll solve. Um, nickel Cn4 2 minus. So 2 minus is the charge on the complex. So x minus 4 is equal to minus 2. X is equal to minus 2 plus 4, which is plus 2. So plus 2. So you guys have solved it. So the option B is the right answer. Nickel is in plus 4 state, and that's the option where nickel is in the highest oxidation state. So I'm really happy that you guys are able to answer the question and find out oxidation state. So now we will move on to, okay, this question, which among the following, which one is paramagnetic? So like this, we will solve step by step. Okay, tell me the number of unpaired electrons, or tell me if option A is paramagnetic or diamagnetic. Is option A diamagnetic or paramagnetic? Please put it in chat box. Okay, okay, yeah. We will solve this one, and then I think if anyone is not able to answer, they'll also be able to answer the rest of the questions. So first, if we have to look a complex is paramagnetic or diamagnetic, we have to know the number of unpaired electrons, right? So for to know that, first we have to understand what is the oxidation state of cobalt or the metal, and then we'll understand how many d electrons it has, and then depending on the geometry, we will find out, we will fill the electrons, and then we will see if the complex is paramagnetic or diamagnetic. So from this we can see that cobalt is in 3 plus state, right? So cobalt in 2 plus state has D7. So cobalt in 3 plus will be D6. Number of electrons in cobalt 3 plus is D6. And this is an octahedral complex. So we have a T2G EG splitting, and NH3 is a weak field ligand, so there is no pairing. So 1, 2, 3, 4, 5, and then it pairs 6. So now how many unpaired electrons are there? 4 are there, right? So this is definitely paramagnetic. Okay. Now, what about nickel Cl4 2 minus? Is it paramagnetic or diamagnetic? Okay. What about nickel? Option B. Is option B paramagnetic or diamagnetic? Okay, one more thing I have to tell you. So for successfully getting good marks in this course, you need to know the 3D elements. 3D elements and how many d electrons each element has. At least the 3D. Rest of that does not matter that much. So, so you need to uh, either learn it somehow, or I had given a simple like thing where I'll just write the 3D elements: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So in their plus 2 state, these the number of d electrons will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we know, say now we are looking at cobalt 3 plus, right? But if I know that my cobalt 2 plus has d7, and 3 plus means I just have to remove one more electron, which means that it will be 6, right, in plus 3 state. So if you learn this, it will be very easy for you. You can just solve these questions in seconds. Okay, let me check the chat box if anyone has answered. Okay, now let's see if it is paramagnetic or not. Okay, so here nickel is in plus 2 state, right? Nickel is in plus 2 state. Okay, so as I said, nickel in plus 2 state has d8 electrons, and this is a tetrahedral. So we have E T2 states, and Cl is a weak field ligand, so singly fill 4, 5, 6, 7, 8. So this is also paramagnetic. Okay, so now what about um, FeCN6 4 minus? Okay, wait a second. Okay, so actually I made a mistake here. One second. Let me confirm it and then I'll. Okay, so here for nickel Cl4 2 minus, what I did is right. The number of unpaired electron like this will be, this is, one second. Okay, so this is the E and this is T2, and there are two unpaired electrons. So this is definitely a right answer. But what about this cobalt NH3 plus? So here I need to emphasize that whenever the 3D metals are in 2 plus state, then if a ligand like NH3 is a weak field ligand. For 3D metals in for 3D metals in 2 plus state, ligand like NH3 is a weak field ligand. But if my metal is 3 plus, then NH3 becomes a strong field ligand. Because if you remember the spectrochemical series, NH3 lies actually somewhere in the middle of weak field and really strong field ligands. So basically NH3 will change its character depending on the nature of the metal. So if the metal is 2 plus and it is 3D, then NH3 will be a weak field ligand. But if the metal is in 3 plus, that is, I am talking only about the 3D metals, whenever the 4D and 5D metals are there, NH3 or any ligands, all ligands are strong field. For 4D and 5D metals, all ligands are always strong field, they'll always go for pairing. But for 3D metals like this series, in this case, cobalt 2 plus, for cobalt 2 plus or any metal in the 3D series with 2 plus state, NH3 will be a weak field ligand. But if it is a, like for example, cobalt 3 plus, this NH3 will be a strong field ligand. So basically for cobalt, let me take a new slide, one second. So cobalt, cobalt NH3 6 3 plus. So here the cobalt is in 3 plus state, so NH3 is a strong field ligand, right? So this is octahedral, so T2G, EG, And first, and as I said, in cobalt in 2 plus state will have d7 electrons. So cobalt in 3 plus state will have d6 electrons. So we first, since it is strong field ligand, we will go for pairing. 1, 2, 3, 4, 5, 6. So number of unpaired electron is 0. So this is a diamagnetic complex. So whoever answered diamagnetic in the chat box, you guys are absolutely right. I am really sorry for the mistake. I should have emphasized this in the beginning. So basically, this is not a right answer. This is diamagnetic. So you guys also have to be very careful. You always have to look at the oxidation state. If it's a 4D or 5D metal, we can assume that all ligands are strong. They'll always go for pairing. But whenever it's a 3D metal, and then we will have to look at the oxidation state. If the 3D metal is in +2 state, then the normal spectrochemical series will follow. If NH3, ligands like NH3, which comes in the middle of the spectrochemical series, will be considered weak. But if it is like cobalt 3 plus, like in a higher oxidation state, then NH3 will be a strong field ligand. Now, okay, let us do for FeCN6 4 minus. So please put it in chat box. Option C, is it diamagnetic or paramagnetic? That is pretty straightforward. I think we have solved it many times also. For your reference, I am keeping this number of d electrons at the +2 state. Okay. Okay. So we will discuss. Okay. FeCN6 4 minus. So oxidation state of Fe here is Fe2 plus. Right? So it is like x minus 6 minus 4, x is equal to +2. So Fe is 2 plus and Fe2 plus has T6. And Cn, as we know, is a strong field ligand. So, and it is an octahedral complex. So T2G Eg, we will go for pairing. So 1, 2, 3, 4, 5, 6. So this is also a diamagnetic complex. There is no unpaired electron. But what about K2 nickel F6? This is a diamagnetic or a paramagnetic? Here you should be really careful about the oxidation state of the metal. And what is the identity of the metal, 3D, 4D or 5D? Please put it in chat box. Option D, is it paramagnetic or diamagnetic? Okay. Anyone else wants to answer? Okay, so I'll say let's work together. Okay. So first we'll find out the oxidation state of nickel, and since there are two potassium outside, the overall charge on the complex is 2 minus. So x minus 6 is equal to minus 2, x is equal to minus 2 plus 6, which is plus 4. See, nickel is in plus 4 state, which is a highly oxidated, which is a high oxidation state, right? So here, even this fluorine will act as a strong field. So whenever the metal is in a very high oxidation state, then the metal has much more, what does it mean? Whenever the metal is in high oxidation state, it means that, 4 plus means that I have removed 4 electrons from the nickel. Now the number of electrons compared to the nickel 0 is less, but the actual nuclear charge is same for both, right? Nickel 4 plus and nickel 0 had the same nuclear charge, but the amount of nuclear charge felt by each electron is different now. So nickel 4 plus has lesser electrons, 4 electrons lesser than nickel 0. Therefore, the attraction from the nucleus to the electron will be much more stronger now. Because of that, the nickel 4 plus will be a much more smaller ion, therefore it will interact also much strongly with the ligands. Therefore, this crystal field will be splitted also very much. Therefore, even with a weak field ligand like F, the nickel 4 plus will act like a strong field ligand. So even a weak field ligand like F will act like a strong field ligand in the presence of a high oxidation state metal, for example 4 plus. So here we will solve. So in nickel in plus 2 state has D8. So plus 4 means we remove 2 more electrons, which means that it is D6 now. The same case, T2G pairing will happen. So there is no unpaired electrons. So this is also diamagnetic. So there is only one paramagnetic, that is nickel Cl4 2 minus. Is this clear?
Yes, ma'am.
Okay. So we'll move on to the next question. Huh. So this one also, I should say that this is an organometallic compound. This does not come under your, your course at all. But since it's a 18 electron rule, and most of the time they will only ask about this CP ligand. This is called CP, cyclopentadienyl. So I'll just try to solve this. So consider the 18 electron rule as a guide and determine the value of N in the following compounds. So whenever we consider the organometallics, organometallics is when a metal has a direct bond with carbon. So basically here this C5 H5 is also having direct metal carbon bond with rhodium, and carbon monoxide also has a direct metal carbon bond with rhodium. So in these cases we should not consider the oxidation state. We will consider the metal in its zero state. So here I said that rhodium, okay, let me say rhodium actually comes in the cobalt group, like cobalt, rhodium, yttrium. Yeah,
Ma'am, do we need to remember the 4D and 5D configuration elements also?
most of the time I don't think they will ask that, but something like this, it is um, like if you know the transition metals, it will make your life much more easier. But I would say at this level, at least learn the 3D elements. 4D and 5D are not important uh, at this level, but 3D for your course is much more important than 4D and 5D. This, as I said, is not related to your course content. That's why I think maybe rhodium has come. But since they are in the same group, whatever the cobalt, the number of electrons in cobalt 2 plus, that will be the same for rhodium. So if I know that they are in the same group, it helps. So cobalt in its 2 plus state has D7. So cobalt in 0 state will have 2 more electrons, right? So it will be D9. So rhodium will also have D9. So now the 18 electron rule says that for organometallic compounds, the total number of electrons in that compound will be 18. So now the question is, how many number of carbon monoxide should be added to get 18 electron? So here they have not given the number of carbon monoxide. So we have to find how many number of carbon monoxide should be there to satisfy this 18 electron rule. So as I said, rhodium will be considered as M0 here. So 9 electron will be coming from rhodium. Then CP has different modes, like it can be eta 5, eta 3 or eta 1. This eta 5 means it is giving 5 electrons, eta 3 means it is giving 3 electrons, eta 1 means it is giving 1 electron. So whenever we have 5, 3, 1, we will take the corresponding values. Here we have 5, so we will take 5 electrons, and each ligand, each neutral ligand will give 2 electrons. Carbon monoxide is a neutral ligand, so this will give 2. But we don't know how many, right? So 2 into n is equal to 18. So now n plus 5 is 14, 9 plus 5 is 14, plus 2n is equal to 18. Or 2n is equal to 18 minus 14, which is equal to 4, and n is equal to 2. So the answer is 2. So you just have to find like know the number of electrons in rhodium and how many electrons each Cp and carbon monoxide are giving. But as I said, this is not related to your course, so I don't think you have to learn this. But since it was in assignment, I have just solved it.
Okay, ma'am.
Okay. Huh. So this is also a similar question like we discussed one before. What will be the electronic configuration for the complex K3, Fe, Cn6? So first you'll have to identify the oxidation state, and then you'll have to look at the geometry, and then you have to accordingly fill. So can you put it in the chat box which is the right option? After that we will discuss. What is the right answer for this? What will be the electronic configuration for this complex? Please put it in chat box.
Ma'am, can you explain the former one?
Which one? The that we explained just now. That
Ah, yeah.
rhodium.
Yes.
Okay. This one, right? Okay. One
Yes,
second.
ma'am.
Okay. So as I said, this is not related to your course, but you will learn this more in the organometallic course if you have one. But for organometallics is something where there is a direct bond between the metal and carbon. So if you look here, this C5H5 is something known as CP or a cyclopentadiene. I'll just draw the structure. This is not a neutral ligand. So here the metal is like this. So all these electrons can coordinate with this metal. So basically we have 5 carbons and there will be 5 this direct metal carbon bond.
Okay.
Uh, yeah. Now carbon monoxide is also like that. We have metal like this. So there is a direct metal carbon bond. So in these cases, there is something called as an 18 electron rule. It means that whenever there is a metal carbon bond, that is in organometallic compounds, there will always be 18 electron. This is the 18 electron rule. This should be followed. This is compulsory for organometallic compounds. But only exception is 16 electron rule. This is for square planar complexes. But if for most of the time this 18 electron rule is followed, but sometimes for square planar exception is the 16 electron. So since they have mentioned that 18 electron rule as a guide, we know that this complex, the total number of electrons in this complex should be 18 electron. But the question is to find out how many carbon monoxide are there. We know that from the complex, rhodium will give 9 electrons and this Cp will give 5 electrons. But we don't know how many carbon monoxide are there. That is what we are finding here. So each carbon monoxide should give 2, but how many we don't know. That's what I am giving here as n. So 9 is coming from rhodium, 5 is from Cp. So 9 plus 5 plus 2 into n. 2 is coming from 1 carbon monoxide, but I don't know how many. That is why I have kept n here. So basically, if you add up 14 plus 2n is equal to 18. 18 is coming from this 18 electron rule. Then therefore 2n is equal to 18 minus 14, which is 4. So n is equal to 4 by 2, which is equal to 2. Okay, that's why we got this answer. Is it clear?
Yes, yes, ma'am. Thank you.
Okay. Okay. Yeah. So yeah, you guys have been answering option D, right? Let me check. Okay. So we'll solve this first and then we will see if option D is the right answer or not. Okay. So K3 is given. So the overall charge on the complex is FeCN6 3 minus. If we find out the oxidation state of Fe here, x minus 6 is equal to minus 3. So x is equal to minus 3 plus 6, which is plus 3. So Fe is in 3 plus state and the ligand is Cn. So anyways, this is a strong field ligand. Even if Fe was in 2 plus state, this will be a strong field ligand. Definitely pairing will happen. And this is an octahedral environment. So definitely it's T2G EG configuration. And Fe 3 plus, right? So Fe in 2 plus state, I'll show you. Fe in 2 plus state has D6 electrons. So Fe in 3 plus state means it has Fe2 plus has d6 electron. Fe3 plus means I have removed one more electron. So Fe3 plus means d5. Right? So now I'll just pair 1, 2, 3. Now we will do pairing because it's a strong field ligand. 4, 5. So basically it should be T2G 1, 2, 3, 4, 5, EG 0. Definitely option D is the right answer. Well done. Okay. So I hope you don't have any doubts here. If you have
No,
any doubts, you can ask. Okay. So similar question only. What will be the right answer? The electronic configuration of cobalt F6 3 minus and copper NH3 6 2 plus. What will be the answer here? Please put it in the chat box. Then we will discuss. I'm sorry, actually, I had some internet issue. I'll just reshare my screen. Okay. Okay, can you please once again put in the chat box? What was the answer? Because I could not see what you guys have written. Okay. Anyone else wants to answer?
ma'am.
Yeah.
Ma'am, the table which you have given for the 3D elements,
Mhm.
in the plus 2 state, they were like from 1 to 10. Then in plus 3, it was 0 to 9. Then can we write it for plus 4, plus 5, plus 6, like giving it first 2 as 0 and then 1 to 8, and then 3 zeros and again till 1 to 7?
Yes, you can write, but you don't have to remember all this. You just have to
Hmm.
remember any one.
Okay.
Whatever is comfortable for you, just remember that.
Okay.
Hmm. Okay. So we will solve cobalt F6 3 minus. So the oxidation state of cobalt here is 3 plus. So cobalt 2 plus is D7, cobalt 3 plus will be D6. Now we will solve, okay. So this is octahedral. Now this is cobalt 3 plus and F is a rather like a weak field ligand. So there won't be any pairing. 1, 2, 3, 4, 5, 6. So this is T2G 4, EG2. Now, what about copper? Copper is in 2 plus state and this is a D9 configuration. One second. Yeah. So this is a D9 configuration and it is also an octahedral complex. So basically T2G and there won't be any uh, there won't be any pairing because this is a weak field ligand. So 1, 2, 3, 4, 5. Then it will go for pairing 6, 7, 8, 9. So T2G6, EG3. Yeah, option C is the right answer. So I hope no one has any doubts in this question, right?
Yes.
Okay, okay, great. Now we will solve next question. Huh. This is an interesting question and I think you'll be able to solve even though the question is a bit lengthy. So I'll read out the question. Given the molecular formula of the hexa coordinated complexes COCl3NH36, COCl3NH35, COCl3NH34. So these complexes are given. The question is if the number of coordinated NH3 molecules in 1, 2 and 3 respectively are 6, 5, 4, then the oxidation state of cobalt in 1, 2 and 3 are respectively. So Please put in chat box what do you think the answer is. Then we will discuss. Okay. What about others? Okay. Okay. Anyone else wants to answer? Maybe I'll wait one more minute to see if anyone else is answering. Okay. Okay. So we will discuss. So everyone has said B. Let's see if D is the right answer. So they have said that in one, the coordinated NH3 molecule is 6, and this is 5, this is 4. So now let me say why they have specifically said the coordinated NH3 molecules. See here, they have just written the molecular formula. They have not written the complex formula. Complexes, when we write, we give this bracket most of the time. And in this question, they have given coordinated NH3. Coordinated means inside the complex, there is this many number of NH3. So they have also said that the same number of NH3, but just the coordinated meaning is that this is directly coordinated to the metal. It is not outside the complex. It's not there for charge neutralizing or anything. This is directly linked, coordinated with the metal. So the first one has 6 NH3, second one has 5 NH3, third one has 4. But does this affect the oxidation state? No, right? Because all of these complexes have 3 chlorines and the only number of NH3 is changing. But NH3 is neutral,
Ma'am,
right?
Cl is uh, it is a
Yeah,
counter ion, no?
I did not understand.
Ma'am, Cl is a counter ion, no? It is outside the coordinated sphere, no?
No, actually, yes, yes, true,
Okay.
true. Yes, because they have not given. See, if Cl was inside, then the charge would be, you know, 0, right? Because if there is nothing outside. No, no. Let me think about it. So to be x minus 3 is equal to 0, x will be plus 3, otherwise it's x minus 3. No, no. Here I think the chlorine is inside only. Here they have also said that it is hexa coordinated complex. Hmm, yeah. Now
But
there
if
is
it
another.
was out, then we would have taken it as +3, no? Means
Yes.
coordination number.
Hmm. Just give me a second. Let me think about it.
Yes.
1 second. Yeah, got it. I got it. One second. I'll just reshare my screen. Huh. So now you have to really read the question. One second. The question is given the molecular formula of hexa-coordinated complex. So for all these complexes, the coordination number is 6, right? So, and they have not given any complex formula. So either Cl3, Cl can be outside or NH3 can be outside. But the second part of the molecule question says that the first molecule has 6 NH3, the second one has 5 NH3, the third one has 4 NH3. So now the first one, if you see, if there are already 6 NH3, it's already a hexa-coordinated complex, which means that this Cl3 is counter ion.
Okay.
Yeah. So here, the second compound we have 5 NH3, but the question is hexa coordinated, right? So one more Cl will be there to make it hexa coordinated, and Cl2 will be counter ion.
Okay.
Now, yeah. So in the third one we have 4 NH3, so two more Cl will be here to make it hexa coordinated, and one Cl will be counter ion. Right? Now we will calculate. So for the first one, cobalt NH3 6 Cl3. This Cl3 is counter ion. So if we remove Cl3, what will be the charge on the complex? 3 plus. So cobalt is also in 3 plus state, right? This
Okay.
x plus 0 is equal to 3 plus and x is equal to 3. So cobalt is in 3 plus state. So this is 3 plus. Now we'll look at the second one. So here it is CONH3 5 Cl, and there are two Cl2 outside. There are two Cl outside, which means that the overall charge on the complex is 2 plus. So now what is the oxidation state of cobalt? X minus 1 is equal to 2, x is equal to 2 plus 1, 3. So this is also plus 3. Now,
Yes.
yeah, what about this option 3? I mean the compound 3. So it will be cobalt NH3 4 times Cl2 and 1 Cl is outside. So here x minus 2 is equal to, so here this will be plus 1, that will be the overall charge. So x is still plus 3. So option D is the right answer. I think
Okay, ma'am.
all of you chose right. Yes. Yeah, good. So option D is the right answer. I think it is clear, right? Now is it clear?
Yes,
And,
ma'am.
okay. Yeah. Huh. So now we'll refresh upon the crystal field theory. So using crystal field theory, identify from the following complex ions that shows same spin-only magnetic moment. So not spin-only magnetic moment. Can you put in the chat box? I'll just give you the formula for spin-only magnetic moment. Root of n into n plus 2. You have any doubts? I think someone is speaking.
Excuse me, ma'am.
Yeah.
For the former one, which one is right answer, ma'am?
Yeah.
Examine
Former one,
coordinated complex. First one.
this one, no, option D is the right answer.
Okay.
Plus 3, plus 3, plus 3. Each are in plus 3. So should I explain again?
No, 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 ma'am. I
Okay.
don't want.
Option D is the right answer.
Thank you, ma'am.
Okay. So here the spin-only magnetic moment equation is root of n into n plus 2 Bohr magnetron. So use this where n is the number of unpaired electrons. Use this formula and let me know in the chat box which is the right option. I'll give
Ma'am,
you
we
a
check
couple of
unpaired
minutes.
electrons through only the oxidation state of the metal, no?
No, I did not understand the question. Okay.
Ma'am, do we consider the number of unpaired electrons from the oxidation state of the metal, no? If it is CO3 plus, then we are going to look at how many unpaired electrons CO is having, or after pairing with F6 we are going to look
Now, after first we will look at what is the oxidation state. Then they will find out how many d electrons that metal has. Then they will look at the nature of the ligand. If it is weak field or strong field, then we will fill up the. Then only we can understand. Then we will fill up. Then only we will be able to understand how many unpaired electrons are there. Always
at.
draw this T2G EG levels, fill up, and then it will be much more easy, and you will not make any mistakes. Yeah. So anyone wants to answer? Okay, I'll give you a couple of minutes to solve. So let me give you another clue. Iridium is, I think, a 5D element, and it is in the cobalt group. Cobalt, rhodium, iridium. So the same trend of cobalt will be followed in this iridium also. Okay. 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 Anyone else wants to answer it? I'll give you maybe one more minute. Okay.
Ma'am, in the C option, after in the coordination sphere, the oxidation state is written as 2 plus. It would be 2 minus, no?
This one.
Huh.
No, this is Fe will be in 2 plus state. The overall charge is 2 plus, but
Okay.
water is a neutral ligand, right? So this will
Okay.
be x plus 0 is equal to 2 plus. So Fe is in 2 plus state,
Yes, yes, I
right?
know.
Okay, maybe we'll solve this question. So cobalt, the first option, I mean the compound A, COF63 minus, in this case cobalt is in 3 plus state, right? So cobalt in 2 plus state has D7, so cobalt in 3 plus will be having D6 electrons. So now this is for cobalt 3 plus. Even though it is cobalt 3 plus, since F is like a very weak ligand, we will be still having, we won't be having any pairing here. But like in a previous question we discussed nickel 4 plus with F. In that case we will have pairing because nickel is in 4 plus state. This is CO3 plus, so it's comparatively a lesser oxidation state. In this case, since also because F is like a very weak ligand, we won't be having pairing here. So this is octahedral complex T2G and D6. So 1, 2, 3, 4, 5, 6. So the number of unpaired electron here is 4. Now we will look at B, which is iridium Cl6 3 minus. Here iridium is also in plus 3 state. Now I already said iridium belongs to 5D. So irrespective of the ligand, definitely it will go for pairing. So iridium 3 plus will also has d6 electron. 1, 2, 3, 4, 5, 6. So number of unpaired electron is 0. Right? Okay. So now we will look at C, which is Fe H2O6 plus. This is in Fe2 plus state. So Fe2 plus has d6 electrons, and it is a T2G EG splitting because it is octahedral, and H2O is a weak field ligand, so there is no pairing. So 1, 2, 3, 4, 5, 6. So number of unpaired electron here is also 4. So since the number of unpaired electron is same for both, definitely this option, this C of F6 3 minus, that is complex A and complex C, will have the same spin only magnetic moment, right? Because N is same here, so the value will also be same. We don't have to calculate the spin only magnetic moment here. We just need to identify which one will have the same. So just by looking at the number of unpaired electron, we can say. So basically the answer is A and C. So option C. So whoever answered A and C, very good. So I think this is clear, right?
Yes, ma'am.
Okay.
Ma'am,
This is a, yeah.
Ma'am, the weak ligands, according to the spectrochemical series, will behave like strong ligands after the 4D and 5D series, no?
Yes, all every time in 4D, 5D metals, all the ligands will behave as if a strong field ligand. The reason is that the 4D and 5D metals are much more larger than the 3D metals. Since they are larger, that repulsion from the incoming ligands will also be larger. Therefore, that basically the interaction is more there, right? That is why the splitting is much more higher than the 3D elements. So for all the 4D and 5D elements, irrespective of the weak or strong field ligand, there will always be a higher delta O. That is why we will always have pairing. But for 3D elements, as I said, depending on their oxidation state, the character can change.
So, ma'am,
But
oxidation status +4 or +5, then we will consider the substance or the ligand to be strong and then it will pair, no?
yes,
Okay.
yes. But like for ligands like NH3 is almost near the strong field. In that case, even cobalt 3 plus is fine. In that case, even cobalt 3 plus, with cobalt 3 plus, NH3 will act like a strong field ligand. But see, for example, here F is like on the other side. F is one of the weakest ligand. In that case, cobalt 3 plus, even if cobalt 3 plus is there, that pairing won't happen. But if it is nickel F4 plus, nickel 4, if it is a nickel 4 plus state, I mean the metal is in a higher oxidation state like +4 +5 and all, in that case the even the weakest ligand will act like a strong field ligand. Is it clear?
Yes, ma'am.
Okay, so one second. Yeah, someone is raising a hand. Yeah, Sujada, do you want to ask me something? Okay, maybe unknowingly pressed. If you have any doubts, you can ask me directly, or if you are not able to tell me, you can. Okay, one second. Am I still audible?
Yes, ma'am.
Okay, yeah.
Ma'am,
So if,
can you hear
yeah,
me?
yes, yeah, I can hear you.
Crystal field splitting value is 10 dq, we say no, ma'am. Then how
Yes,
can we
yes,
say more splitting and less splitting?
yeah. So one second, I was just kicked out. One second.
I can't hear you, ma'am.
One second, one second. I'm having some issues. My laptop is getting hanged. One second. Yeah. So your question is, when we say 10 DQ or some DQ, so why will this splitting change, right? So let me explain that. I think I had some slide here. Yeah. So see, for these complexes, these are the delta splitting, which is experimentally obtained. So if the delta was same, they should be having the same values, right? But it is not the case because the interaction with each metal and each ligand is different. So the extent of this splitting, that is what we call the delta of, or when we write zero point 0.6 delta O or 5 dq or 6 dq, that the value of dq or delta O is not fixed. This delta O depends on how much splitting is there, right? This is not a fixed value. This will change depending on the nature of the metal, identity of the nature of the ligands, oxidation state, and the number of ligands. Is it clear? See, here also it is there. Like when the splitting is happening, we have this, whatever the splitting is there, that is called the delta O or 10 dq, right? So it can be either minus 4 dq. If you say with respect to dq, this T2G will have minus 4 dq contribution for each electron, and EG will have plus 6 dq, right? This dq or delta oct is not a fixed value. This depends on, this changes for each complex. So here, that is what I have shown here. For these complexes, they have different delta values because they split in a different extent. For example, here titanium is in 3 plus state. Here also titanium is in 3 plus state, but the ligand fluorine is a much more weak field ligand than the water. Therefore, the titanium water complex will have much more interaction and much more splitting. That is why this delta is much more high here, right? And here vanadium is in 3 plus state, vanadium is in 2 plus state. So this 3 plus vanadium will have much more stronger interaction with water ligand. Therefore they will be having much more, splitting, that is delta O or dq, what we say. That is why it has got a like higher delta value than the vanadium 2 plus state. Is it clear? Okay, I think she has left the meeting maybe. Okay, if she comes back we will discuss it again.
Ma'am,
Yeah.
ma'am, the questions that we are doing today will be shared on the
Hmm.
portal.
Yes, yes. Actually,
Okay.
I like if you look at the portal, there'll be something called a problem solving session. There'll be a separate tab. So whatever we discuss in the class, that I am recording actually. So that recording will be available, and there will also be these questions. Whatever I have given in this slide, that slides will also be there. But
Okay.
sometimes when I record, sometimes I am not able to record your responses, so that questions may not be clear, but whatever I am saying is recorded. So I
Yes.
think the week 1 class, when I recorded, I could not record your responses, but in week 2 I could solve that. Your responses were also recorded, but in week 3 I don't know what happened. So I am actually using a third party recording app, maybe because of that. So this time I have again tried in a different way. I hope that your voices are also recorded, but anyways my voice will be recorded, the screen is also recorded, so you'll be able to see what we have discussed in the class so far.
Okay.
Yeah. So we will move on to discuss whatever we were discussing. One second, let me share the screen. Yeah, this one we discussed, right? Okay, so yeah, the question is the magnetic moment of an octahedral cobalt 2 plus complex is 4 Bohr magnetron. The electronic configuration of the complexes. So they have given that the number of unpaired electron will be somewhere around 4. So whenever they say the magnetic moment of cobalt 2 plus whatever complex is 4 bm, we can, it generally comes around like 3. If it is 3, it will come around 2, like a approximate amount we can guess. So from that also we can identify what kind of configuration this metal has. So I think you'll be able to solve this. Please put it in chat box. Which option is the right option? So please put it in the chat box. Okay. Okay. So we will solve. 1 second. So they have said that octahedral CO2 plus complex. So CO2 plus is T7 and octahedral means there should be T2G EG kind of splitting. Uh, so we can do in two ways, right? We don't know whatever the ligand accompany is a strong field or weak field. So we will arrange in both ways, one with pairing and one without pairing. So 1, 2, 3, 4, 5, 6, 7. This is with without pairing. I should say without pairing. Weak field. If it had a weak field ligand, it will be the case. Then next case is 2, 4, 6, 7, right? Strong field. Okay. Now, which will be the right answer? For that, from this, as I said, from this we can almost guess that there'll be like 3 unpaired electron. Otherwise, we can just solve from the equation also the magnetic moment. So from this, what if the number of electron was unpaired electron is 3? Then what will be the mu s value? It will be 3 into 3 plus 2. So 3 into 5. So root of 15. So around, so root of 16 is 4. So around 4 it will come, right? Then here it will 4 bm. Here number of unpaired electron is 1. So mu s will be 1 into 1 plus 2. So root of 3. So this will come around 2, right? So basically from this we understood that this will be the right configuration. Therefore T2G, how many electrons we have? 2, 4, 5. So T2G 5 and EG2. So is this clear?
Yes, ma'am.
Okay. So this one we already solved. So now I think maybe we solved this question. I'm not sure, but anyways we will solve it again. Consider the two complex nickel H2O6 2 plus and nickel NH3 6 2 plus. What is the right statement? Are complex A is diamagnetic and complex B is paramagnetic, or vice versa, or are both paramagnetic or both diamagnetic? So please put in the chat box which is the right answer. Okay. Okay. So yeah, we will discuss now. So NH Ni H2O6 2 plus. In this case, nickel is in 2 plus state. So in 2 plus state, it has D8 and this is an octahedral complex. So T2G, Eg, and also water is a strong weak field ligand, so there is no pairing. 3, 4, 5, 6, 7, 8. So this definitely is paramagnetic. Now we look at this one. Again, this is nickel is in 2 plus state, and NH3, and it is D8. NH3 is also a weak field ligand. 1 second. So again we'll have no pairing. 1, 2, 3, 4, 5, 6, 7, 8. So this is also paramagnetic. So option C is right. So all of you are right actually. Good. So I hope there are no doubts in this question, right?
No, no.
Okay. So now this question. The correct spinal structure of CO3O4 is. Here also the trick is to note CO2 plus and CO3 plus, how they will interact with oxygen. See, oxygen is also is somewhat like NH3. It's not a weak field or a strong field ligand. It is somewhere in the middle, right? So you have to now decide what will be the nature of CO2 plus 2 plus's interaction with oxygen, and what will be the nature of CO3 plus's interaction with oxygen. So these clues I have given. So maybe we'll solve in step by step. So first tell me what is the CFSE of CO2 plus in this complex. CO2 plus in a tetrahedral oxygen arrangement. See, as you know, this spinal structures have this offer, which is like a tetrahedral arrangement. So CFSE of cobalt 2 plus in tetrahedral with oxygen. What is the CFSE? Please put in the chat box. I'll give you a couple of minutes. Okay. Okay. So maybe we'll solve this question. Okay. So as I said, cobalt. So I think you all remember what spinels were, right? So there'll be three metals. So one metal will be in 2 plus state, other two will be in 3 plus state, right? And whenever the CFSE of M3 plus is higher than the CFSE of M2 plus, this will be having a normal spinel, and this M3 plus will be in octahedral vacancies, and M2 plus will be in tetrahedral vacancies. And we have the opposite case where CFSE of M2 plus is higher than the CFSE of M3 plus. In that case, we have the inverse spinel, and the M2 plus will be occupying octahedral sites, where M3 plus will occupy both tetrahedral and octahedral, right? So now we will solve with what kind of spinel it is, and according to that we'll be able to answer. To identify what kind of spinel, we have to first calculate the CFSE of both M2 plus and M3 plus metal ions, then we will be able to identify, right? Okay, so yeah, so first we know for in this spinel also we have one two cobalt 2 plus and two cobalt 3 plus. So cobalt 2 plus will have D7 electrons, cobalt 3 plus will have D6, right? And I already said this is in a tetrahedral oxygen arrangement, and oxygen is neither, it is somewhere in the middle. It is not a weak field ligand, it's also not a strong field ligand, it is somewhere intermediate. Okay, so with cobalt 2 plus it acts like a weak field ligand, and it is tetrahedral, so we have a E T2 state, T E T2 configuration, right? And D7 electrons, D7 is there, so 7 electrons are there, so there won't be any pairing because for 2 plus cobalt 2 plus oxygen, the oxygen acts as a weak field ligand. So 1 2 3 4 5 6 7. Okay, so now we will calculate the CFSE. CFSE for this will be minus 0.6 each, this will be plus 0.4 each, right? So here the minus 0.6 into 4 plus 0.4 into 3. This will come around minus 2.4 plus 1.2, so minus 1.2 delta T, right? Okay, so
Yes.
now we will, yeah, so I'll just write only that and then I'll remove the remaining part. Yeah. So we already calculated CFSE for cobalt 2 plus is minus 1.2 delta T. Now we will calculate for CFSE for cobalt 3 plus. So cobalt 2 plus was D7, so cobalt 3 plus will have D6 electron. And now we have to look at what kind of interaction it will have with oxygen. Oxygen, as I said, is an intermediate ligand, and cobalt is in 3 plus state. Therefore, it will have a stronger interaction. Therefore, we will have pairing. So again, it is tetrahedral. So T2E we have and 6 electrons. Since we have a higher, stronger interaction, it will go for pairing. So 1, 2, 3, 4, 5, 6. Right. So now if we calculate the CFSE, it will be minus 0.6 into 4 plus zero point 0.4 into 2. So minus 2.4 plus zero point 0.8, it comes around minus 1.6 delta T, right? So cobalt 3 plus's SCFSE will be minus 1.6 delta T. So definitely cobalt 3 plus's CFSE is much more greater than cobalt 2 plus. Therefore, this is a normal spinel, right? So cobalt 3 plus will be in octahedral state. Both cobalt 3 plus will be in octahedral state, and cobalt 2 plus will be in tetrahedral state. So tetrahedral vacancies. So which is the right option? Option A. Cobalt 2
Ma'am,
plus in tetrahedral. Yeah.
why did we pair the electrons in CO3 plus?
Yeah. So, do you remember where we were pairing for nickel 4 plus, then even when we had, no, I should not say nickel 4 plus, cobalt 3 plus with NH3, when we had NH3, I said that it is not a weak field or a strong field ligand, it is somewhere in the middle. It's like an intermediate ligand. Since cobalt is in 3 plus state, that interaction is much more higher now, and when cobalt is in 3 plus state, now my NH3 becomes a strong field ligand, then we will go for pairing. So similar situation is there. Oxygen is also an intermediate ligand. So whenever cobalt 2 plus is there, it will act like a weak field ligand. But whenever we have a higher oxidation state like cobalt 3 plus, then it will go for pairing.
Okay.
Yeah. So Option A is the right answer. Cobalt 2 plus is in tetrahedral vacancies, and other both cobalt 3 plus are in octahedral vacancies. So I hope this is clear, right?
Yes, ma'am.
Okay. So let me just check chat box. Okay. Okay. So this is also a direct question. The spin-only magnetic moment of titanium 3 plus ion is. Please put in the chat box what is the answer. I'll give you a couple of minutes. Okay. 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 We'll solve. Okay. So right. So scandium, titanium, vanadium, and so on. So titanium in its plus 2 state will have D2. Plus 3, this is plus 2 state. In plus 3 state, it will have D1, right? So
Yes.
basically, yeah. So let me just draw the 5d orbitals. I only have one electron. So the spin-only magnetic moment is n into n plus 2, and n here is 1 because there is only one unpaired electron. So 1 into 1 plus 2 is equal to 3. Root 3 is 1.73 bm. So everyone has answered rightly. Good. Very good. I think we are near the last question. So the complex that shows orbital contribution to the magnetic moment is. So I hope you remember what kind of orbitals will show orbital contribution, which set of orbitals will will show orbital contribution, right, to the magnetic moment. So please put in the chat box, then we will have a discussion. Which is the complex that shows orbital contribution to the magnetic moment? I'm sorry, I was skipped out. I'll just share the screen. Okay. Please put in the chat box what will be the answer. So no one wants to answer, or you guys answered and I was kicked out of the meeting because I am not able to see any answers. I'll wait for 2 more minutes, and then no one is answering. I'll just discuss. Okay. 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 Then we will discuss because you need explanations. So, so the question is, which complex will show orbital contribution to the magnetic moment? So orbital contribution will come only if the electrons are present in T2G. If they are in EG, it won't be there. And also, there should be at least one empty space so that the electron can go. If there are no empty spaces of for the same spin, it can't be go. So here there will be the orbital moment, our contribution will be there. So if it was like this in T2G, then there is no orbital contribution. And if it was something like this, then there is a orbital contribution because this downspin electron can still go here. That vacancy is still here. So now we will discuss for each complex. So this is copper is in 2 plus state. So copper in 2 plus state has D9 electrons and it is octahedral. Water is a weak field ligand. So T2GEG, there is no pairing. 3, 4, 5, 6, 7, 8, 9. So this the unpaired electron is in EG, there is no orbital contribution. If there was any space in T2G, we could have checked, but there is no the T2G level is completely filled. There is no vacancies. In EG, there is a vacancy, but it is not possible for orbital contribution because I'll just refresh the memory why there is no contribution from EG because other orbitals like dxy, dxz and all can be inter just by rotation of dxy I'll be able to get dxz. Just by rotating it I'll get d yz and so on. But if I rotate dz square, I will not get dx square minus y square. So that is why Eg orbitals, whenever there is an electron Eg, it does not show orbital contribution, but T2G will show. So definitely this one will show this will not show orbital contribution. So let us look at nickel. Nickel is also in 2 plus state. Nickel in 2 plus state has d8 electron. It's also with water and octahedral environment T2GEG. There is no pairing. So 1, 2, 3, 4, 5, 6, 7, 8. So here also the unpaired electrons are in EG, but it is all electrons are like there are no vacancies, right? In T2G also there is no vacancy, in EG also there is no vacancy, but even if EG had vacancy, it still won't contribute. So for this complex also there is no contribution. Now we look at nickel Cl4 2 minus. So nickel here is in 2 plus state. Now the Cl is a weak field ligand, but the important thing to note here is that the coordination environment is tetrahedral in nature. So we have E T2. So nickel in 2 plus state will still have D8. So 1, 2, 3, 4, 5, 6, 7, 8. So this was the E, this is the T2. So in T2, this electron, okay, 1 second. This is T2, this is E. So I'll just highlight in a different color. So this downspin electron can go here and here. So there is definitely the orbital contribution is there, right? So definitely this one has orbital contribution. Now what about chromium? The next complex, chromium is also in 2 plus. So chromium in 2 plus state has d4 electron. So again and it is octahedral environment. So and it is water. Uh, there is no pairing. So 1, 2, 3, 4. Again this is symmetrically filled. There is no space for any electron in T2G, so there is no contribution. Here also it is Eg, even though there is a vacancy, it is Eg, there is no mual contribution. So this is also not there. So only nickel Cl4 2 minus has the orbital contribution. So is it clear now?
Yes, ma'am.
Okay. Yeah. So I just need to I'll just refresh on yawn tolerant distortion as well. Then we will wrap up this class. Yawn tolerant distortion is also similar, uh, but here EG will have a strong contribution, strong, strong yawn tolerant distortion, and T2G will have a weak yawn tolerant distortion. Here also for symmetrically arranged, that is whenever there is no vacancy or whenever there is partially or completely filled, there is no JT. For example, if I have something like this, 1, 2, 3, there is no JT here. Then or if I had something like this, definitely JT is there but weak JT. This is also called static. I think it is. Okay, I'll just go with this. So it is also, so for whenever the whenever there is a space in the T2G, it is a weak yawn tolerant distortion. But if it was something like this, then the unpaired electron is in EG, it can go here. So here we have strong yawn tolerant distortion. But if it was something like this, there is no yawn tolerant distortion, right?
Ma'am, so half filled and fully filled doesn't have Jantel distortion.
No, does not have. Okay, I hope this is clear. I just wanted to refresh. So
Ma'am,
in this
once,
case, yeah, you
ma'am,
are
once
asking
can you
something.
share your email ID? If I had
Yeah,
a doubts, I'll ask.
yeah, sure, sure. This is my email ID cy21d501 at iittp.ac.in. I'll put in the chat box 1 second.
Thank you, ma'am.
iittp.ac. Yeah. So I have put my email ID in the chat box. If you have any doubts, you can always ask me.
Okay.
Mm, yeah. So I think we are done. Let me check. Yeah, as since I was talking about Deontology distortion, um, normally if you want to see a strong iontology distortion, there should be some some electrons in Eg. So normally it happens for complexes like copper complexes, like copper 2 plus complexes. So it has a D9 configuration, so there will be an unpaired electron here, there will be a strong iontology distortion. So whenever you look at a copper 2 plus with a copper 2 plus complex, then most probably it has an iontology distortion. um then let me see. ah yeah, we will solve this one also, I think. This will be the last question. The zero magnetic moment of octahedral K2NiF6 is due to what configuration? Is it low spin or high spin? Here also you have to be careful about the oxidation state of the metal. That is a clue. I'll wait. Please put in the chat box which will be the answer for this question.
Ma'am, K2 is out of the coordination sphere, no?
Yes, yes. K2
Okay.
is outside actually. This question is a bit. Just clarify it 1 second. K2 is outside. K2 NiF6. Okay, yeah, we will solve it. So K2NiF6. So the overall charge on the complex is NiF6 2 minus. The oxidation state of nickel will be X plus minus 6 is equal to minus 2. X is equal to minus 2 plus 6 is equal to plus 4. See, nickel is in plus 4 state, and like we discussed in a previous question, nickel in plus 4 state will make even the weakest ligand a strong field ligand, right? So definitely pairing will be there. So, and also this is an octahedral complex, therefore it is T2G configuration. As I said, there will be pairing. And what will be the number of electrons here? Nickel in 2 plus state has D8. So 4 plus means we are removing 2 more electrons, so it will be D6. So 1, 2, 3, 4, 5, 6. So this is a low spin D6 nickel 4 complex, right? Is this clear?
Yes, ma'am.
Yeah. So there are some questions which I have not included in which I have not discussed. So this is one of those questions. This discusses about the associative dissociative pathways. These are about the reaction mechanisms of organometallic compounds. Not even for transition 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 complexes. These are organometallic complexes. Then this is a actually a separate topic. This is called clusters. Whenever we have like a clusters will be like, we'll have different structures like tetrahedron or octahedron, or different macro bigger structures. In that cases we can have multiple metals, and these metals can have multiple bonds, metal bonds. So there is a specific formula, so that is not required for this course, so I won't be discussing it, because you don't have to learn at this point, because you won't be understanding why we are doing this, because this is like a very different topic from uh, whatever is in the scope of this subject. Same goes for this question. And this one also, this is actually related to transition metals, but I don't think this course discusses the reaction pathways or the reaction mechanisms of transition metal complexes, therefore this is also not required. So I won't be discussing these three questions. Yeah, so if we have any other doubts, we can have a discussion. If you have any doubts, you can put in chat box as well. Otherwise, if you don't have any doubts, we will end the class. Okay, you don't have any more questions, right? Okay. Yeah, so I wish all of you, a great exam. I hope all of you pass this course with flying colors, and I thank all of you for your for attending the class every Tuesday. And I should specially thank Tanushree, because she has been there from my first class, and I'm actually really happy to see her in all of my classes, and she has been a really active participant. She responds to all my questions, she writes in the chat box. I am really happy. And also I have seen like many repeating participants like Priya, then I have seen Simran. They are also very much interactive, and I have seen them also in multiple classes, answering questions in chat boxes, asking doubts. I'm really happy. So I just wish the very best to all of you. So if you have any doubts, I have just given my mail ID. You can just follow me up in that. I'll try to help you.
On behalf of all the students, we thank you all, ma'am. Your
Thank you.
teaching
Thanks.
is so good. We are enjoying a lot. You are
Thank
clear
you.
so much of doubt. What are all the doubt we had in inorganic chemistry? Basically, you are explained well. Thank you. Thank you so much, ma'am.
Thank you. Thank you so much. It means a lot to me also. So yeah, this is our last class. Maybe in some other courses in the future, maybe we will see again. Okay. So wish you all the best. Bye. Good night to all.
Thank you, ma'am. Bye.
Yeah.
Thank you,
Thank you.
ma'am.
Bye.
Good night.
Bye.